Hello, everyone. Today we are going to start our lecture 4 and talk about algebraic properties of matrices and matrix inverses. We're going to start with algebraic properties. Very quickly, matrices are going to have very similar algebraic properties as normal numbers, which means that like they are going to follow commutative and distributive law for addition. For example, matrix A plus matrix B is going to be same as matrix B plus matrix A, right? And the minus kind of going to be same. Also, for addition, we are going to have associative law, so it's going to be A plus B plus C equals to A plus B plus C, right? We can put parentheses which way we like. Also, we have associative law for multiplication. So if you have A multiplied by B and by C, you can do it this way, or you can do it this way. Multiply A by product of B and C. We do not have commutative law for multiplication, so works only for addition, unfortunately. But we in previous section already seen why it doesn't work, because actually, like when you add two matrices, they must be the same shape. For multiplication, everything is a little bit more complicated. We also have distributive law, right? Distributive law works on both sides, so it means that if you have we actually keep the order of matrices. If you have matrix A multiplied by the sum of matrices B plus C, you can distribute it and have A multiplied by B plus A multiplied by C. Because matrices do not commute for multiplication, we are going to have also different side of this distributive law. If you have a sum of matrices multiplied by matrix C on the right, remember matrix A over here sits on the left, right? This is the right multiplication. And we can also distribute this matrix C, and it's going to be A multiplied by C plus B multiplied by C distributive law, right? Uh, what else? Well, scalar multiplication means that you can multiply matrix by a scalar, and the scalar does not really care on which side you put it, left or right, and has also very same distributive laws and associative laws. Sorry, my plus does not really look like a plus. Think parenthesis, this is plus B. Okay, now let's talk a little bit about special matrices. We do know that for normal numbers, we have two special numbers, number 0 and number 1. Do we have similar numbers or matrices, similar, which are having similar function as number 0 and 1? Yes, we do have actually 0 matrix. We're going to label it as 0 matrix, but actually that's going to be whole class of matrices which can be something like this. For example, just one number 0. This is matrix of size 1 by 1, and it has only one 0 entry. Can also be a matrix, for example, 2 by 1 and have two 0 entries. Or it can also be something like this, matrix 2 by 2, which has all zeros. The key point here is that all entries of the matrix are supposed to be 0. And matrix can have a different shape. We are going to call all of them like 0 matrix, and sometimes we are just going to draw 0, but we are going to mean 0 matrix, which means that it can be like 4 by 2 by 2 matrix having entries as zeros. What are going to be the properties of 0 matrix? Well, it's similar properties to real or to any kind of normal numbers we used to have. For example, if you add 0 to any matrix, you are going to have the same matrix. And you can do it on the left or on the right. So 0 plus matrix or matrix plus 0 is not going to change the matrix. Property number two, subtraction of matrices. If you take matrix and subtract it from itself, you are going to get a zero matrix. Here, zero is not just our normal zero. It can be matrix 2 by 2, for example. Yeah. Then what is going to happen if we multiply zero matrix by matrix A? Or if we multiply matrix A by matrix 0. Well, remember, by properties of multiplication, we are going to take, for example, a row of matrix 0, which is going to have all zeros, and multiply by a column of matrix A, which could be different numbers, right? If we multiply all those zeros by all these different numbers, we are still going to get a bunch of zeros. If we add them together, we are still going to have 0. So the result is going to be 0. This 0, again, is not just a number, it's a matrix, and probably this 0 matrix is not going to be similar to either this one or this one, because you remember multiplication actually changes the shape of like matrix. Well, of course, it's not always going to do it, because you can just multiply two square matrices and eventually you are going to get another square matrix, which is going to have same dimensions. Okay, what else is going to be last property I want you to kind of look at? What is going to happen if you multiply 0 by A, and this one is not matrix but scalar? I'm going to label this one as matrix. So this 0 is actually a matrix. This one is a scalar. Scalar means just a number, right? If you multiply scalar by matrix A, remember, by the rules, you have to multiply every element of matrix A by that 0 scalar, which is going to produce all zeros. And of course, it's going to work in, like, if you change the order, multiply scalar on the right. So kind of very good. Number 5. What is going to happen if you have a scalar now multiplied by matrix A and you have the result is a 0 matrix? What can we say about this scalar or a matrix? Well, in world of normal numbers, we know that if you multiply number A by number B, we get 0. It means that either A equals 0 or B equals 0. There is no escape to have 0. If these both are non-zeros, they are going to produce non-zero answer. What is going to happen to matrices? Remember that here A is a matrix and C is a scalar. I think A is scalar. So is it going to be still true? Well, imagine that you have kind of numbers here that you multiply by something and get all zeros. Remember that scalar actually multiplies every element by that. So, well, I'm going to show a little example here because I'm going to draw a conclusion, but I don't want to do a formal proof. Imagine that you have a scalar C and you multiply it by some matrix A. I'm going to use just 2 by 2 matrix, but it can be anything. Sorry, it was supposed to be. Sorry. Somehow my eraser is too wide. Scalar C, matrix A11, A12, A21, and A22. So the result is going to look like 0, 0, 0, 0. Well, what we multiply C by element A1, and we are going to get 0. Here, C and A1 are just regular numbers. They are not matrices anymore, and they follow this law. Like if you multiply something by element and get 0, that means that either C is equal to 0 or A1 equals to 0. I'm just doing the comparison, just the first element. So C by A11 equals 0 means that C equals 0 or A11 equals 0, right? If we continue doing the same comparison, we are going to get the similar statements for all elements, either C equals 0 or element equals 0. Let's imagine that C equals 0. Then elements can have any values, but multiply all zeros by any values, you are going to get 0, 0, 0 matrix, right? Let's imagine that now all elements are equal to 0. Then we are going to have any scalar multiplied by the 0 elements, still going to give us 0 matrix, right? So we have a conclusion that if we do have expression like this equals to 0, then either C equals to 0 or A is going to be a 0 matrix. So this 0 is not actually normal 0. You'll probably ask me what is going to happen if, for example, C equals 0, but some elements of A not equal 0. Well, we are going to deal with this case, right? So it's not kind of, if C equals 0, it's not necessary that elements of matrix A are all non-zero. Maybe one of them is non-zero. Or, well, you know. So that's going to be a last statement about zero multiplication. I want to also say that if you do have product of two matrices, I'm going to use a different color, equals to 0. Maybe I should erase this, because this is not going to be like a true statement. If you have a product of two matrices equals to 0, it is not necessary that one of these two matrices is equal to 0. For scalar in a matrix, that's going to be the law. So if you multiply scalar and matrix, either matrix is equal to 0 or scalar. But for product of the matrices, just because product is more complicated, it's not going to be true that if the product is equal to 0, then either of these two matrices must be equal to 0. It can't be like if matrix A is equal to 0, it's probably multiplied by appropriate matrix C and going to get 0. But you can have non-zero matrices and still have 0 as a result. A little homework I'm going to ask you to prepare for the next class is to find A, which is not equal to 0, and B, which is not equal to 0, such that A multiplied by B is still going to be equal to 0. Okay? Kind of try to figure out. That's your choice. Like you do like your create an example which is going to actually be counterexample to the statement that either A is supposed to be equal to 0 or B is supposed to be equal to 0. Remember, there is one way to disprove the statement is to find counterexample. Just find counterexample. Okay? Okay, we are done with zero matrix and we are going to move to identity matrix. Remember that besides 0, we do have a special number, which is going to be 1. And for 1, which properties do we have for regular numbers? 1 multiplied by any number is giving you the same number. So, for example, 1, I'm going to label identity matrix. So if you have 1 multiplied by any number, it's still going to be the same number. So 1 multiplication does not change number. Are we going to have anything similar in the world of matrices? So do we have a special matrix I, which you multiply by any matrix A and get back matrix A again? To understand what kind of matrix it can be, we first need to think, oh, like how multiplication works. What I'm going to do, guys, first, I'm going to consider one example of multiplication with two 2 by 2 matrices. Imagine that we have a matrix which consists only out of ones on the main diagonal. It's 2 by 2 matrix, so it has 2 ones and kind of some other, like some zeros on other positions. And we have 2 by 2 matrix, 1, 2, A, 2, 2. Sorry, A, 2, 1, supposed to be A, 2, 1, and A, 2, 2. And let's try to see how multiplication is going to work here. For example, we multiply the first row by the first column. When we do this, we're going to see that because in the first row, we have 1 in the first position and all other zeros. It's going to give us a product, which is going to be just the first element. the second element is going to be multiplied by 0. And if matrix is bigger than like 2 by 2, but like 3 by 3 or 4 by 4 or 5 by 5, if it has structure of 1 in one position, it's actually going to give you result the number of the second matrix in the same position. Let's see how it works for the second row. Second row has 1 in the second position, right? So when you multiply it by the first column, it's going to give a result as a multiplication only of the second element, which is going to be exactly what it was in the previous matrix. You can understand that if we repeat the process for column number 2, you are going to have same 1 multiplied by 1, 2, a1, 2, and 0, 1 multiplied by a22 is going to give you a22. So you see that this shape of the matrix is going to not change matrix A by which you multiply. Again, this happens because we designed this shape, or like say I did know that this shape can work like that. And if the matrix is different, like bigger or smaller, well, smaller, you can have just one smaller matrix is going to be still going to give same result. What we do know about this matrix, it's supposed to be a square matrix, number one, and it's supposed to have ones on main diagonal only. So if this is matrix with more rows, it's supposed to have more columns. It can be matrix 5 by 5, 6 by 6, 7 by 7, but it's supposed to be the same shape. Matrix C does not supposed to be square matrix. I was using square matrix, but can be something else. Okay. What is going to be major property of such matrix? That if you multiply this matrix by any matrix A, you are going to get matrix A back. And if you multiply matrix A by matrix I on the right, you are still going to get matrix A. What is interesting, guys, because matrix A is not necessarily supposed to be a square matrix. This identity matrix and this identity matrix are not necessarily same square matrices. Let me show it to you on example of non-square A matrix. If your A matrix is a square matrix, of course, two identity matrices are going to be same just because multiplication requires same size of amount of columns and rows to multiplication just exist. Let me show you. Imagine that matrix A has dimensions of 2 by 3. Okay, I'm not going to put elements. Instead of elements, I'm going to put circles. Imagine that it has 3 elements in each row. So if I want to multiply this matrix by identity matrix on the left, I suppose, because I have 2 elements in a column, I suppose to have 2 elements in a row. This way, multiplication will be possible, right? Remember, we multiply row by column. So in this case, identity matrix is going to be square matrix. And it's still going to return back this shape of the matrix, 0, 0, 0, 0, 0, 0, something like this. Now, imagine now different situation. I'm still going to have same A matrix elements. And again, these are not zeros. I'm going to make them dark circles. They are just elements. I don't want to write down indexes. It's kind of because I'm using computer for my whiteboard. It's really hard for me to write down small numbers. Now, if I want to multiply it on the right, now I'm going to have my rows coming from matrix A, and they have 3 elements. So my columns are also supposed to have 3 elements. Let me actually make this side a little bit longer. So my columns supposed to have 1, 2, 3 elements. So this way I will be able to multiply, right? My column supposed to have 3 elements. So like I can multiply this column by this. And well, since I want to get identity matrix and I know that identity matrix must be a square matrix, I'm going to have matrix which is going to have now 9 elements and be a matrix 3 by 3. Here we have 2 by 2 matrix. And here we are going to have 3 by 3 matrix. Okay. But the result of this multiplication is still going to be this matrix with 6 elements, very same A matrix. But again, it's not necessary that this identity matrix and this identity matrix, when we write them down on left and the side, left and the right side of the matrix A, are the same matrices. We'll just kind of try to experiment. Pick up any like 6 random numbers and multiply it by identity matrix like this. You are going to get the correct result. Okay, so what is going to be next? Next is going to be interesting theorem about reduced row echelon form. Remember last class we learned how to work with Gaussian elimination, and I'm going to the proof of this theorem is very, very short. So I'm just going to sketch maybe the proofs. Imagine that we do have reduced row echelon form. I'm going to label it as a theorem. Reduced row echelon form. So remember that this is reduced row echelon form. Reduced row echelon form is made by special rules, right? We take a matrix and apply matrix operations, and we turn the first element in the first row into 1. And if that element is already 0, we are going to scan like the whole matrix and figure out like which row has non-zero first element, and then put it on the top and turn it into 1. And if all rows have 0 elements, we are going to move to like the second element. Like we are going to repeat operation, and the same operation is going to work, and it's going to allow us to build ones in like one position to the right from the previous row. Well, if it's possible, of course. Sometimes we are going to have the row of zeros. Well, the theorem is going to tell us that if you have reduced row echelon form of a n by n matrix, I'm going to label a n by n matrix, then this reduced row echelon form either identity matrix or has a row of zeros. So either it's going to when you apply all these operations, either it's going to become identity matrix and it's going to look like this, 1 0 0 0 0 0 1, and like until you reach the very end, or it's going to have a row of zeros and it's going to look like this. Maybe one over here also, but somewhere here it's going to be a row of zeros. I'm going to label either this one or that one. That's IN, and this is a row of zeros. Row of zeros. Oh, well, how do we prove it? Well, if the matrix does not have a row of zeros, if matrix has like some element in every row, it's going to mean that every row is going to have one leading one. And this leading one is going to sit on a diagonal position because there are just n rows and each is going to have one, and each one is going to be one position to the right from the previous. So all matrix is going to be populated with ones in the main diagonal. That's one option. Or maybe like other situation that one row or two rows, or we don't know how many rows, is going to have no ones anywhere. And then it's going to have row of zeros. The theorem tells that it can be just one row of zeros, or we don't know how many. It can be more than one row of zeros. But you cannot have any other option here. Why? Because we constructed our method either like have like only ones like this, or have some ones and like maybe one empty row. So we don't have any other option. We cannot have, for example, one in the second position here and one in the second position in the last row. trying to explain like what are their options. For example, let's consider this last row. And if it's not row of zeros and not a row looking like this, like in this matrix, for example, we have 1 in this position, in the second position. We can always eliminate it using this one, just like subtract the second row from this last one. And it's going to be 0 row because so our method is constructed that way. So we either end up with identity matrix as a row, reduced row echelon form, or with matrix of with row of zeros. Okay, eventually we are going to use it somewhere. For right now, we are just going to remember that we have this. Well, a little deviation from actual matrices, two solutions of equations. Maybe not the best way to do it, but well, let's remember this. Now I'm going to talk a little bit about inverse matrices. Remember that with normal numbers, we do have inverses. What are inverses? Well, in normal numbers, if you have number A multiplied by number B and it equals to 1, we're going to say that B actually equals 1 over A. We're going to call B inverse of A, right? Example, like, for example, I'm going to use just numbers to kind of maybe show it more. For example, 1 over 3 is actually, let's use just a number 3 multiplied by b equals 1. Then b is inverse of 3 and it equals 1 over 3. Well, for matrices, actually, there are also inverses with some limitations. Not all matrices are going to have inverses. So I'm going to introduce a definition first. Definition. If matrix A is a square matrix, and B is a square matrix of the same size. Of the same size. Then, or and, better to say, A multiplied by B equals identity. And B multiplied by A equals identity. Then we are going to call matrix B inverse of matrix A. And we are going to label it as A inverse. A to the negative 1 actually means A inverse. Well, let's kind of look at this definition and see what it actually includes. Well, first, guys, matrices must be square. So non-square matrices has no chance to have an inverse. Well, why does it happen? Because for non-square matrices, remember, the rules of multiplication are going to require another matrix have a different shape. Well, to be to make multiplication process possible. So we are going to limit ourselves to square matrices. For square matrices of the same size or the same shape, we can kind of do multiplication on the left and on the right. So what this multiplication tells us, like definition tells us, you multiply matrix A by some matrix B and get identity matrix. If you compare it to normal numbers, you multiply number A by number B and get 1. Well, then B is inverse. The difference of this definition from normal numbers is that you do have a second part of this definition. So B multiplied by A in opposite order is still identity. Why do we need this? Because we know that the product of matrices does not commute. So it's if you have matrix A multiplied by matrix B equals identity, it's not necessary that B multiplied by A is going to be equal identity as well. Well, eventually we are going to prove that. It's going to be the proof statement. But for right now, for definition, we are just going to say that like if we do have inverse, it does not matter on which side of matrix A we multiply it, it's still going to give you identity. If matrix does not have inverse, we are going to call such matrix singular matrix. I'm going to introduce it as a new definition. Definition. If such B does not exist, then we are going to call matrix A singular. Well, too bad, right? So for normal numbers, we also do have one number for which we don't have inverse, right? It's number 0. If you multiply 0 by any number, you cannot get 1, no matter how you try. For matrices, we remember that you can multiply two matrices and they are not necessarily must be 0 to give you 0. So we are not going to call A 0 matrix. We are going to call it singular matrix. Just, well, again, because multiplication does not commute and you can have two non-zero matrices multiplied and give you 0. We are not going to call matrix A 0 matrix. We are going to call it singular. But the idea is that's kind of similar to the idea of 0 matrix, a 0 number. Like, I'm going to prove a little theorem, which is going to tell me that if B, if I have two matrices not equal to each other, but they both are inverses A, then B is equal to C. So you cannot have two different inverses of the same matrix. This is theorem of uniqueness of inverse. So inverse is unique. If matrix has inverse, this is only one inverse. There are not like two different inverse, which is going to have the very same properties. Let's prove this theorem. So let's imagine that we have matrix B and matrix C, and they are not equal to each other. They are both inverses of A. Let's prove that they are equal to each other. What I'm going to have, guys, I'm going to have matrix B multiplied by matrix A. Because it's inverse of matrix B is inverse of matrix A, it's equal to I, right? Also, I can have matrix A multiplied by matrix C, and because C is inverse of A, it also must be equal to I. Maybe I should not put equal sign here. I mean, they are equal. If this is identity and this is identity, these two identity are equal to each other. We are dealing with only square matrices, right? What I'm going to do, I'm going to multiply this statement by C on the right. What I'm going to have? Well, from the statement on the right, I know that A multiplied by C is identity, so this product is identity. Also, I know that any matrix multiplied by identity is a matrix itself. So what I'm going to have? I'm going to have B multiplied by identity equals C. I know that B multiplied by identity is B matrix because identity is such matrix that you multiply by any and get the same. So my final statement is B equals to C. So my assumption that B is not equal to 0, but they both can be inverses of A is wrong. So I proved my theorem. Okay. So that is going to tell us that there is only one inverse, and we can introduce a special sign inverse, which is going to be A inverse. There are not going to be like two different matrices with the same properties of inverse. Okay, now, how do we find this inverse? Actually, there are going to be several methods. And first, guys, we are going to start with a formula of inverse matrix for matrix 2 by 2. For matrix 1 by 1, everything is kind of clear. So imagine that we do have example number 1. It's going to be matrix 1 by 1. Imagine that we have matrix which consists out of only one number. What is going to be inverse of this? Well, we remember that both matrices must be square matrices, right? And it's supposed to give us identity. And in this case, that's going to be just matrix which consists out of one element. And if we multiply these two, we are going to have A multiplied by B equals 1, from which we can make a conclusion that B, which is kind of element of inverse matrix, is 1 over A. So for 1 by 1 matrix, everything is clear, right? Let's move to 2 by 2 matrix. And imagine that we have matrix with 4 elements. I'm going to, guys, I'm going to label these elements not with our traditional scheme of E11, E12, E13, but I'm going to label them with all different letters, A, B, C, and D. So this is typical 2 by 2 matrix. Actually, guys, I'm going to make a suggestion or a formula for inverse matrix. And what we are going to do, we are just going to multiply it by this matrix A, which is like random numbers A, B, C, D, and show that it's going to be identity. Because we do know that inverse is unique, we are going to say, well, that means that this is inverse. I know that it's not the best way to find out inverse, but other ways are much longer and I don't have time to do that. Okay, so my suggestion is that inverse of matrix A is going to look next way. 1 over A multiplied by D minus B multiplied by C. It's a scalar. And it's going to be multiplied by a matrix consisting out of switch of A and D. So you put D here and A here, and minus in front of C and minus in front of B. Well, not very complicated mnemonic formula. What is the major condition? Denominator must not be equal to 0. Just check if we are going to get identity matrix when we multiply this. And that's going to be our like verification of the formula, because we already proved that if we do have a matrix which we multiply and we get like identity, that's going to be inverse because inverse is unique. Okay, guys, I'm going to do one check. I'm going to multiply my matrix A inverse by matrix A. And I'm asking you to do the second one, A by A inverse. Oh, okay. Okay, so A inverse equals, this is the number, I'm going to put it in front, A D minus B multiplied by C. And now I'm just going to write down matrix A inverse, which is D minus B minus C A, and my original matrix A, B, A, B, C, D. I'm just going to do straight multiplication. I'm going to keep the coefficient in front. A multiplied by D minus B multiplied by C. And my first element is going to be produced by this multiplication, right? First row by first element, I have A by A. That's going to give me A squared. And B, I know, not A. Actually, handwriting is not good. And I wrote D over here, but well, how do I have A in here, here, over here, and also A over here? This is D, right? Remember? So sorry, I'm going to write down AD, and that's supposed to be AD and minus BC, minus BC. That's my first element. My second element is going to be DB minus BD, BD. Well, we know that DB minus BD is going to give 0, right? Element over here is going to be minus CA. I'm multiplying the second row by first column. Minus plus AC. AC. Minus CA plus AC is also 0. And the last element is minus C by B. Minus C by B plus A by D. A, D. Sorry, I'm writing down at the very edge of my screen. So for right now, I'm going to just copy my coefficient in front, AD minus BC, and copy my elements which are non-zero. AD minus BC, which is exactly the same, right? 0, 0. And if I put AD first for the last element over here, it's going to be still AD minus BC. Remember that if you want to multiply scalar by a matrix, you have to multiply it by every element here, this, here, and here, right? Zeros are, of course, going to give me zeros, but if I multiply, for example, the denominator by numerator here, I'm just going to get 1. This 0 is going to stay 0, and over here is going to be 1. So I get my identity matrix. Again, because we defined inverse as a matrix which you can multiply on the left or on the right to get identity. You need to check the second part of it. I don't want to like spend time on checking this. I just want to like check half of it and leave the second half for you to check at home. Okay, I'm going to consider an example just to see how it works. Okay, and let me just consider something very simple. Example 3. I'm going to consider matrix 1, 2, 3, 4. Right? That's going to be matrix A. According to my formula, A inverse is going to be 1 over 1 by 4 minus 3 by 2. By the way, is it equal to 0? That's 4 minus 6 equals to negative 2, not equal to 0. Very good. Now I have to exchange 1 and 4, so put 4 here and 1 here, and put minus in front of 3 and minus in front of 2. Kind of inverse is given, right? So negative 1 over 2, 4 minus 2 minus 3, 1. Uh, you can always bring the coefficient which sits in front of the matrix inside. You just need to multiply every element by it, right? So for example, 4 over 2 is going to give you minus 2. And minus 2 by 1 over 2 is going to give you 1. And here, unfortunately, nothing to cancel. That's going to be 3 over 2, while the minus is going to cancel. And the last element is just negative 1. So that's going to be inverse. And you can just check if the product is going to give you actually identity. So that was my example. Uh, Now, guys, I think I'm going to take a break at this part. We still have a little bit more of this lecture, but I don't want to make it very, very long. So this lecture is going to have two parts, and we are done with first part. I'm going to do the second part separately. Okay.